All right, so we're going to do the same initial setup right here. We're going to make it a perfectly elastic collision, and there are three techniques. So this video is for technique number 1, then we'll do 2 and then 3. I am making some assumptions that you have watched the imperfect collision already, so I'm going to skip through some of the math explanation, I believe. Well, I guess we'll find out. So momentum is conserved, collision. Perfectly elastic, kinetic energy is conserved. And so we start out with, well, we have the same equation as we did on the last video. We have negative 17 is equal to 5c plus 8d. All right, so there's one. The kinetic energy equation, its initial is equal to final. So we have K initial equals K final. So 1/2 times 5 times 3 squared plus 1/2 times 8 times 4 squared is equal to 1/2 times 5 times c squared plus 1/2 times 8 times d squared. This is just, again, kinetic energy at the 5 kilogram mass plus kinetic energy at the 8 kilogram mass before is equal to the kinetic energy of the 5 kilogram plus the kinetic energy of the 8 kilogram after. And again, using C and D, I guess since it's a new video, I should write this down again. So C is V5 final, and D is V8 final. When we get to technique number 2, why I'm using C and D here, perhaps will make a little bit more sense. All right, so going through the math again, we have 2.5, 9 times, so this was 22.5 plus 64 is equal to 2.5 c squared plus 4d squared, and this becomes 86.5 equals 2.5 c squared plus 4d squared. So very similar process to what we went through before. This technique does have an advantage. It is a lot more math, but there is an advantage to it, which we'll talk about at the end. So as before, I know that C is equal to negative 3.4 minus 1.6 D. And over here, we have this, we can just divide by 2.5. We're dealing with decimals right here. Let's see, so 2.5. So if I divide everything by 2.5, that divides each term by 2.5. What I end up with here is, so plus 1.6 d squared. I have c squared here. And then over on the other side, 86.5 divided by 2.5, 34.6. There's no particular reason why I have to do that. I just like dealing with simpler numbers, and I'm not, since they're rational and finite, I can express these very nicely in decimal form, and so that's why I did it. It's not crucial mathematically to do that. So I have my value for C here, which I'm going to plug into there. So I have 34.6 equals that squared. So that, again, the negative there will get squared away. So we get 3.4 plus 1.6 d squared plus 1.6 d squared. And so 3.4 squared, 11.56. So this is 34.6 equals 11.56 plus 2 times that times that. So 3.4, 1.6 to 10.88d plus 1.6 squared, 2.56d squared plus 1.6d squared. Again, we have a quadratic, so we want to get everything on one side. Let's get everything on the right-hand side. So I have 0 equals, so 2.56, 1.6 plus, so 4.16d squared plus 10.88d plus, I'm now subtracting 34.6 from both sides, so it'll end up being a negative number there. So 11.56, 34.6 minus negative 23.04, oops, not equals, minus 23.04, and that whole thing equals 0. Again, it's a quadratic equation. I need to, in order to use quadratic formula, I set it equal to 0. So if we now use the quadratic formula, I have D is equal to negative 10.88 plus, I'm going to try to write that neatly this time, negative 10.88 plus or minus the square root of 10.88 squared minus 4 times 4.16 times negative 23.04, and that is a 4 there, over 2 times 4.16. So 10.88 squared. So this becomes the square root of 118.3744, and then 4.16 times 23.04 times 383.3856. We add them together, plus square root of 501.76, square root 22.4. It came out very nicely. So I have negative 10.88 plus or minus 22.4 divided by 8.32. I will have two solutions again. Now they both have legitimate meaning here. So 10.88 negative, 22.4 minus 8.32 divided by. So one solution is negative 4 meters per second, and the other solution is 10.88 negative, enter, 22.4 plus 8.32 divided by, and 1.3846, and so on, meters per second. All right, I know we've done something absolutely correct here. One of these solutions is legitimate, one of them is not. For a collision, if we plug into the value to find C, so these are the values of D, C would be, well, we have our formula right there, same as we did last time in the imperfect collision. So I'm going to take that number right there, times 1.6 negative times, and then 3.4 minus, and so I get C being negative 5.6154 meters per second. And if I plug negative 4 in, I better get the right answer there. 4 times, and then we end up with 3 meters per second. One of the solutions is correct for a collision, and one of them is not. So pause for you to figure it out, and I'm going to take a breath here. All right, welcome back. And so we can think about it like last time, as in after they collide, they're not going to pass through each other, and that's what the second solution is telling us. The 8 kilogram is still going in the negative direction, the other one's going in the positive direction. The physical meaning of this is actually they haven't collided yet. Momentum and the kinetic energies definitely stays the same if they haven't touched each other yet, and therefore this is the solution before they collide. And this is how I knew we did something right. The advantage of technique number 1, the big plus for it, is you immediately have feedback whether you've done it right or not. However, and so therefore the correct solution is this one right here. The disadvantage is you're dealing with a quadratic and the math is more complicated. So what we're going to do is for technique number 2, I'm going to go through the derivation for technique number 2 first, and then go through the actual solution. Once you know what the final result of the derivation is, you don't have to derive it every single time. You can just jump straight to the final formula. So my impulse is to ask if there are any questions, but email me if you have questions like with any of these. And that's it for technique number 1 for the perfectly elastic collision.